Okay, so last time we left off after our derivation of, let me make sure I can see this one. Derivation of beta hat, which is, or which we found to be equal to x transpose x quantity inverse times x transpose y. And we're going to do a really quick proof just to show that beta hat is an unbiased estimator of beta. So there's going to be a couple of ingredients that we're going to use in this. So first of all, we're going to use our definition of y. So y, which is a vector of y's, is equal to our beta coefficients multiplied by x, our vector of x's, plus some error term, right? So we could denote these all as vectors, but hopefully the notation is obvious enough. So, and then we have that y hat is equal to x times beta hat, and we have that y, this y, not y hat, y is also equal to x times beta hat plus some error term, right, which is our vector of errors. So we'll actually use this one the most, but these are all important quantities that we'll be working with. So, so if we take the expected value of beta hat, that's the same thing as the expected value, right? We know that beta hat is equal to this. That's the same thing as the expected value of x transpose x inverse multiplied by x transpose. And this would be a y, but I want to do a substitution here. So I'm going to substitute with this quantity is equal to x beta, this is not beta hat, right? Just beta, x beta plus the random error. So if I distribute this quantity into here, then we end up with something like this. The expected value of x transpose x inverse multiplied by x transpose multiplied by x beta plus, this is going to be a repetition because it's just the same distribution, x transpose, and this one times beta. Okay, so we need to remember that we're treating x as a constant, and we're treating the betas as a constant. So what this means is that when we take this expected value, I'm going to go over here, we have the expected value of the constant, which is whatever that constant is. And also note that this is the inverse of this multiplied by the thing that it's the inverse of, so that'll be the identity. So we're going to end up with the expected value of beta, right, plus the expected value of all of these terms. And this first part is just a bunch of constants. So we'll just write this out really quick. Okay, but one of our modeling assumptions is that the expected value of our error term is 0. So this expected value must be 0, which means this whole term is 0. So the only thing that's left is the expected value of beta, which is a constant, and the expected value of any constant is just that constant back. So that's what we're left with. Let's check. Okay. So now that we've found our expected value, now we're going to find the variance of our estimator, variance for beta hat. So what is the variance? Well, before I get myself too deep in, we're going to write down some quantities that we had in the last video that will be useful. So maybe most importantly is that y hat, right, our estimate of y is equal to x multiplied by beta hat, right? And the actual y, right, the y that we don't ever really know, is equal to the actual beta vector, which we also don't ever know, plus some random error term. So I'll go ahead and write the last quantity. I don't think we'll use this one, but the actual y is equal to x times beta hat plus our error vector. So however close we get with our estimate plus whatever the distance between that estimate and the actual value, right? So and then I'll also write this, that we found in the last video that the expected value of beta hat is equal to beta. Write that a little more cleanly. The expected value of beta hat. Okay, so now what we want to find is this quantity. We want the variance of beta hat. So let's start by rewriting things to make our lives a little easier. We know that beta hat is equal to xt x inverse xty, right? And we actually solved for what happens when we replace y with x beta plus eta in our last video. So we'll just do it again really quick here. So let's just say that this quantity is equal to x transpose x inverse x transpose, replacing y with this, x times beta plus eta, right? We do this distribution here, which will cancel everything but that beta term, and then the distribution here, right? So cancels a strong word, but right, you get the identity. Multiplied by beta, so beta plus x transpose x inverse xt beta, right? This whole thing is just equal to, right, beta hat. Maybe that was belaboring the point, but I'm going to go ahead and write that up here in our list of important identities. So beta hat is equal to beta plus x transpose x inverse xt beta. Then I'm going to go ahead and clean this up because we're going to need the space. So, okay, so the variance of beta hat is equal to the variance of this quantity that we just wrote. So is equal to variance of beta plus x transpose x inverse x transpose eta. Now, variances of a quantity in matrix form will come into play. So, I mean, we can just think of it like this. The variance of something in matrix form is just for the sake of remembering. So say we have some random variable q, then the variance of q, right, if q is a vector, multiple quantities, is equal to the expected value of q minus the expected value of q, right, all of that quantity multiplied by q minus the expected value of q, all of that transposed. This should be fairly apparent or recognizable from the scalar version of something, right? If q were a scalar, then the variance of q would be equal to the expected value of q minus its expected value squared, right? And that's all we're doing here. This is just the matrix version of taking that square. So hopefully that's not too ambiguous. Maybe I should do another video on matrix stuff, but for now, we have that this variance can be written as the expected value of whatever is in the variance function, which we've just rewritten as this. So it's this thing right? And then we're going to subtract from it its expected value, which we know to be beta. And then this whole thing is going to get multiplied by the same quantity, but transposed. Okay, so these betas cancel, and what we're left with is the expected value of x transpose x inverse multiplied by eta, and then that whole thing multiplied by x transpose x inverse eta. Sorry, there's an x transpose there. Eta, and this second part is all transposed. So what I want to do is distribute this transpose. So it might be worth it to mention this. The inverse of a transpose is the same as the transpose of an inverse. So x transpose x inverse transpose is the same thing as x transpose x transpose inverse. And it should be pretty apparent that if we take the transpose of x transpose x, we're going to get back x transpose x. So we have the expected value of x transpose x inverse eta, and the transpose of this quantity on the inside. It's going to move this eta to the left, and it'll be its transpose. it'll move this x to the left. It'll be its transpose, which is just x. And we've already covered that this quantity remains the same. All of that inside the expected value. So once again, this whole thing is a constant. This whole thing is a constant. So we end up with x transpose x minus 1 times the expected value of eta transpose. I'm clearly missing an x here. Somehow I just forgot to write it. And then this gets multiplied over here by x transpose x inverse. So at this point, we're going to use an identity or definition that we haven't really introduced yet, which is that the variance of eta is equal to sigma. Rather, it's equal to sigma squared. I mean, we won't use this one here, but I'll introduce it anyway. The variance of E vector is also equal to sigma squared. So how this comes into play is, well, maybe I can just write it out here. So we have the expected value of eta transpose. So in order to find this expected value, we need to know the variance of eta. And it turns out that we know that the expected value of eta is 0. So we can write any variance in matrix form as the expected value of that quantity minus its expected value, right, which is 0, multiplied by that quantity minus its expected value transposed. Should be a transpose here. It should be pretty easy to see that this is just going to be equal to the expected value of eta times eta transpose. So that means, as we've already written out here, that this thing is equal to these are actually multiplied by the identity matrix. They aren't, in fact, scalars. They're a single quantity repeated across the diagonals of the identity. So we now have a scalar multiplied by the identity matrix in the middle of all of this stuff. So we can move the scalar times xt x inverse x transpose, and now we have this identity here, right? And then we have x transpose x minus 1, right? Now anything multiplied by the identity matrix is just itself back, right? As long as things are conformable, and things must be conformable because we couldn't have gotten here if they weren't. So this identity in the middle doesn't actually change anything. So we can see that we have this whole thing here that's going to become the identity. And so what we're left with is sigma squared multiplied by x transpose x inverse. And that is the variance of beta hat.